In question number 23, we have been given two large metal plates which are assumed to be thin. In other words, what we are saying is this length is very small as compared to this length, and also the length which is perpendicular to the plane of the computer screen. One more condition required to solve the problem by the method in the class is that the distance between the two plates, that is this distance, is once again very small compared to this vertical length and also compared to the length of the plate perpendicular to your screen. Now, assuming that these conditions are met, we have derived a general result in the class, and this result is, if you put a net charge of Q1 on the left plate and a net excess charge of Q2 on the right plate, then Q1 and Q2 distribute themselves in approximately the following way. You get a charge on this face of Q1 plus Q2 divided by 2, and the same charge you get on this face. So once again, this is Q1 plus Q2 divided by 2, and the charges on this face and this face can then be computed using charge conservation. So this charge must be, the total charge on the plate is Q2, and that minus Q1 plus Q2 divided by 2 gives Q2 minus Q1 the whole divided by 2, and the charge on this surface can be found in the same way by charge conservation. So it will be Q1 minus Q1 plus Q2 upon 2, or alternatively we know the result that the charges on this face and this face must be equal in magnitude but opposite in sign. So this charge would be Q1 minus Q2 divided by 2. Now in the problem, this plate, the left hand side plate, is called X and the right hand side plate is called Y, and the left hand side plate is given a charge of Q, while the right hand side plate has a 0 excess charge. So in other words, we can use these formulae, the four expressions which we have got over here, to find the four charges on the four sides. Of course, Q1 will be equal to Q and Q2 will be equal to 0, and thus we can find the charge distribution. However, what I will do right now is to derive the answer, that is the charge distribution, by using the method which we adopted in class, that is by first principles. In short, what I will be doing is to derive the answer using the same method that we used to derive this general result, that is Q1 plus Q2 by 2 is the charge on the outer surfaces, etc. So we'll try to do it by first principles so that we can revisit the basic concepts, but in the examination you might want to do it by the formula if you remember it. So our first step consists of assuming that there is a charge of, let's say, Q1 over here and a charge of Q2 over here, and we'll try to find the relationship between Q1 and Q2, and this is done by drawing a Gaussian cylinder in between the two plates as follows. Now, since we assume that the charge on each of these four surfaces is uniformly distributed, and it could be assumed to be an infinite plane of charge because of the dimensions of the plates being large compared to the thickness and also compared to the distance between the plates. So all this goes into concluding that the field lines in the gap would be approximately horizontal like that. Now they could be from left to right or right to left depending on which of these two plates is positively charged and which is negatively charged. Remember, the field lines will go from the positive charge to the negative charge. So using this fact and also using the fact that there is a zero field in the body of the metal conductors because of electrostatic equilibrium, we can conclude that the total flux coming out of this Gaussian cylinder is equal to 0. Now by Gauss's law, if the flux is equal to 0, then the net enclosed charge divided by epsilon naught is equal to 0, and that would mean that this Q in, the net charge which is enclosed in the Gaussian surface, must be equal to 0. Now that would mean that whatever amount of charge I've got over here, let's assume that this charge is positive on the left plate, so maybe I've got a certain amount of charge over here. The same magnitude of charge would be present on this face, on this side, excepting that the charge itself would be negative. Now of course the reverse could be true, that is, over here on the right plate it's possible that I have positive charges, in which case on the left plate within the Gaussian cylinder I would get negative charges. So whatever be the case, it essentially means that Q1, the total charge on this face, would be the negative of Q2, which is the total charge on this face. And so instead of writing the charge on this particular surface as Q2, I can get rid of one variable Q2 and instead I can write it as minus Q1. Now the charge on this side could be got by charge conservation. Remember, the total charge on this plate is Q, and that can't change. The plate is isolated from any other conducting body. So the charge on this side must be Q, the total charge, minus the charge on this side, so minus Q1. That's by charge conservation. Of course, we have to remember that the charge in the excess charge rather in the interior of a metal plate in equilibrium, in electrostatic equilibrium, must necessarily be 0. The only charges present would be on the two surfaces. That's our assumption. We have assumed that the charge here on this face or on this side and this side is equal to 0. So the charges are only present here and here, and the total charge must be equal to Q, and that's why I get the charge on the left face to be Q minus Q1 if the charge on the right face is Q1. By a similar reasoning, the charge on the right side of the RHS plate would be 0, which is the total charge, plus the charge which we have accounted for is minus Q1, so I must subtract minus Q1, and so that's why I get plus Q1. So in other words, the total charge on the RHS plate's outer face would be plus Q1. Now all that remains to be done is to find this one variable Q1, one unknown Q1, and then we can plug it in to all of these four expressions and we get the overall charge distribution. To do so, we consider a point, let's call it P, in the interior of any one of these two metal plates. So I have considered it over here, and we know that at point P, the net field E bar must be equal to 0 bar, and that's of course because point P is in the inside of a conductor which is in electrostatic equilibrium. Now the field at P is because of 4 planes of charge. We are assuming that they are infinite planes of uniformly distributed charge, remember. So there are 3 planes on the left hand side of P. It is this one and this one and this one. Now if I have a plane of charge, I'm assuming the charge is positive as a convention, but the result will work for negatively charged planes too. If it's an infinite plane, then the field will point away from the plane, and the value of the field is sigma divided by twice epsilon naught. This is something we have proved by the application of Gauss's law. Likewise, the field on the left side of the plane would also be the same, sigma upon twice epsilon naught, excepting that it's pointing in the opposite direction. Of course, supposing my charge on the infinite plane is negative instead of positive, I don't have to change my formula. I still assume that the electric field in this region is outward, away from the plane, and the value of the field is sigma upon twice epsilon naught. And while substituting for sigma, of course, we are going to substitute a negative number, and that reverses the direction of the field. That gives you the actual field's direction, which of course will then be leftwards. So I don't have to worry about whether the charge on the plane is positive or negative. The formula still works. Now we can return to our problem where we have to find the electric field at P and equate it to 0, because we know that P is in the inside of a metal conductor in electrostatic equilibrium, so the field must be 0. I'll draw P over here. This is point P, and I realize that there is a plane to the right of P, a plane of charge. It is this plane which carries a charge of Q1 assumed to be uniformly distributed, and so clearly the field because of that plane would be in this direction, and it would be sigma upon twice epsilon naught, and sigma of course of this particular plane is the total charge, which is equal to Q1 divided by the area of that side, which is A, and this of course I divide by twice epsilon naught. That's going to be the field at P because of this Q1. It's not the net field. There are other charges which are going to contribute their own fields, and we'll turn to those charges now. Now the other charges are these 3 planes which are to the left of P, and we know that while evaluating the field because of 3 or 4 or 2 planes, one can actually combine the planes into a single plane by pushing them together. Now I combine them, that is this plane and this plane and this plane. I just push them together and I find the field because of them. Note that when I combine them, it becomes a single plane, and the total charge on that plane will now be given by Q minus Q1, which is the charge over here on this plane, plus the charge on the second plane is Q1, and plus the charge on the third plane is minus Q1. So naturally these charges won't play any net role. The excess charge residing on the resulting plane would be simply Q minus Q1, and this would give rise to a field to the right at point P given by sigma. Note that it is Q minus Q1 divided by the area is A, and this of course I divide by twice epsilon naught. Now these are the only 2 fields acting at point P, and we are aware that the net field at P is equal to 0. So of course the fields these two fields, the leftward field and the rightward field, must balance. So I equate them, and in the process this twice epsilon naught cancels and A cancels, and what I'm left with is the equation Q1 equals Q minus Q1, which would then give me Q1 equals Q divided by 2. And when I substitute Q1 equals Q by 2 in the four charges Q minus Q1 and Q1 and minus Q1 and Q1, then the final charge distribution I get is, I get a charge of Q by 2 over here, and I get a charge of Q by 2 over here, and minus Q by 2 over here, and here I get a charge of plus Q by 2. That's the final charge distribution. And then the questions given, the sub questions given, are very easy to answer. The first sub question is to find the charge density at this particular surface, and that's going to be, the total charge is Q by 2 and you divide it by A, and that's Q divided by 2A. B part is to find the field, the electric field, at a point to the left of the LHS plate. And as we know, we can find the net field at this point by pushing these charges, these four planes of charges together and combining them to get a single plane. And if I calculate what is the total charge on that single plane, I get Q by 2 plus Q by 2 is Q, that's of course this charge, and minus Q by 2 plus Q by 2 is 0, that's of course this charge. So the total charge on the plane is actually Q, and therefore I have a single plane carrying a charge Q. The area is A, and although I'm saying it's a plane should have infinite area, but remember, we are doing an approximation. What we are doing is approximating that the large surface is actually a plane. So the total charge will be Q, and when I divide it by the area, I'm essentially dividing by A. That's the value of sigma. And then if I use the formula sigma divided by twice epsilon naught, I get my field. So my field is going to be, sigma is Q by A divided by twice epsilon naught, and that's Q divided by 2A epsilon naught in the leftward direction. Of course the direction could be rightwards if Q is negative, but I don't have to worry about that. Likewise, the electric field at a point in between the plates would be got by pushing together the planes on the left hand side, namely this plane and this plane. So I get a single plane which carries a charge Q, and further pushing these two planes together would get me a single plane which carries no charge at all. So I have to really ignore that plane. So I'm left with a single plane carrying a charge Q on the left of this point. So the charge density is Q by A, and of course I have to divide the charge density, that is divide sigma by twice epsilon naught to get the electric field, which is of course Q upon 2A epsilon naught, and that electric field is pointing in the rightward direction. So that's of course the answer of part C. And point D asks us, or rather part D asks us to find the electric field at a point to the right hand side of the system. So once again I combine the four planes, and what I am left with is a single plane carrying a charge Q. So my charge density sigma is Q by A, and if I divide sigma by twice epsilon naught, I get the electric field. It's Q divided by twice A epsilon naught, and the direction is rightward by convention. Q, if it is negative, of course the actual direction would be leftward.